You can easily replace this block with an inverter, with a 5-phase inverter, okay? Now, once we have got, and these are simply current sensors, H7, H8, H9, H10, these are simply current sensors. And we take that current sensing, I feedback A, B, C, D, E, you can take it back to the microcontroller, and then you can run through the type 3 amplifier in the microcontroller and control the motor. Okay, so here,
they are not competition signals, huh?
See, this is what we have done here is, this will be a commutation signal if I put a PWM block here. I have removed, all I need to do here to have a commutation signal. So this is my duty cycle coming in, DA, okay, which is this point here. So if I take the signal and compare it with a PWM, I get PWM signal. And if I have a switch, I can feed it to here. So only I have to add these two elements to convert it from there to here. Because this here is still the duty cycle signal, which is generated through the error amplifier. Pardon me?
I mean, duty cycle into gain to get the minus voltage to plus voltage. That's what you have just put up here as a block. Instead of
duty cycle into
particular gain to get VDC minus VDC plus.
Yeah, the transfer function of the inverter. So you have to look at it on what is the transfer function of the inverter. The transfer function of the inverter is this. So it is D here, and this is minus VDC by 2, and this is plus VDC by 2. So when D is 0, you have 0 voltage across the binding. Right? And when the D is 100%, you have maximum available bus voltage. So if I look at the inverter, if I look at the inverter, see this here may be 36 volts. Okay? So since this is 36 volts and your neutral is going to be roughly at 18 volts, right? The available voltage is only VDC by 2. So across the binding, you are putting VDC by 2. So the transfer function is like that for the inverter. So you take the inverter and replace it with this block so that you can get much bigger data on the motor side. To be able to do this is great because otherwise this allows you to do torque speed curve, which is very critical information. Otherwise you don't have torque speed curve. There's no way for you to figure out what is. So if you can feed in the correct model of the motor, which will show you how we have done it. If you can feed in the correct model of the motor, then you have something useful.
Yeah.
Right? So what we have did was, we did finite element analysis. With the finite element analysis of the motor, we were able to figure out the variation of KE, variation of the torque effect. Okay, so let me show you how we have done that. So we have, so you have understood this part. Now here is some manipulation we have done. What we have done is taken each of the currents, okay, and we have introduced this block called And in this block, okay, basically this is an absolute block, right? This is an absolute block. Okay, so what we do is we take the current. So the current in the winding, we take it and we make it absolute. What does that mean? That means that it is going to be, so the output of this block essentially is so this is your current, and then absolute is like this, right? Yeah. It just you do absolute value, right? Positive value, because what you're trying to do here is you take all of this TA, TB, TC, TD, and TE, and you are trying to calculate estimate of torque. Okay, you're trying to do an estimate of torque because torque is dependent upon the motor current. Okay, so why are you doing this estimate of torque? You're not doing it for any other reason except to calculate KE. Okay, now what happens to KE? KE, okay, according to when you do finite element analysis, KE is going to show you this. This is ideal KE, and this is your current. Okay?
V and is it torque constant or
Dikm constant, right?
then that must be speed, no?
Instead of current.
Good question, right?
It should be speed.
Yes. So in a motor with 100% efficiency, KT,
No.
or I should say proportion. If you want to be precise, I'll say proportion.
No.
Why not?
KT is torque constant.
So you do the
K is the vacuum
Okay.
effort.
all right. What is your output power?
N into T.
Huh?
N into T.
Okay. N into T. So which is torque times speed.
Or EB into I.
Huh?
EB into I. Dikm into current.
Back EMF,
Into current.
back EMF, K omega into current. Okay, so can I do this? Torque is what? KTI times omega. So K is equal to KT.
Oh, one or the other.
They're the same,
Okay.
right? Now what happens is K and KT are the same. They are the same relationship. Okay, they are basically the same. So normally what happens is it goes like this.
KT.
Both KE and KT.
Yes, same.
They'll go like this.
No. Why did you assume some non-linear?
We are assuming non-linear.
Which non-linear?
That is, as you increase current, okay, your KT goes down and your KE goes down. Okay, that is what we are assuming. So this is what we are trying to. So this table here, E table is a voltage source. Basically, we make a table based on FEA value, finite element analysis. Based on finite element analysis, we have this table here. Let's say we display this value only. So this is the table. It's a big table, but this is the table.
Table of what?
Table of saturation. How KE and KT saturate with current. Now what we have done is, because we cannot do it directly with current, so we have done all these manipulations to have.
What? That is all understood.
Right.
So, isn't this simulation, so suppose if I get a motor, how do I fill all these figures?
You have to design one.
Ah,
Design.
we need.
Design for this.
Motor manufacturers give you detail.
But see-
Motor manufacturers gives a separate.
See, motor- They'll give you linear details. They don't give you the non-linear details. They'll give you the linear operation of the motor.
But you are not supposed to compete in the linear region.
But that's the beauty of electric bicycles. Electric vehicles, you want to operate in a non-linear mode because that region of operation is very small. So I can afford to have that inefficiency for a small period of time if I can saturate the motor and I don't have to increase the size of the motor. Because if I don't live with that non-linearity, then the motor size becomes 2 or 3 times. But whereas electric vehicles, they are limited duty cycle vehicles, right? So you say, okay, let me introduce a non-linearity that allow me to shrink the size of the motor so that I have overall smaller engine size or smaller motor size.
But inefficient.
Only at that point of time.
Short span of time.
Only at that point of time where you're accelerating, right? Where you're accelerating and the point of time you spend in acceleration is very small, 1 second, 2 seconds.
No, see, when non-linearity is there, efficiency is poor. Okay, torque is less, no acceleration. Why to pump current?
You have to meet that acceleration.
You know you are not getting.
You will get if you
See, when you pump the current, saturates, no torque, then you are wasting.
No, you're still getting torque. You're getting less torque. See, let's say 10 amps of my current gives me 10 Newton meters. 20 amps give me 20 Newton meters. 30 amps gives me 28. 40 amps give me 35. Right?
it's not full saturation. It's not full saturation.
No, it's not full saturation.
It's between linearity and
See, electric motors, what is premium?
what is that?
What is the premium in the electric motor?
I would
Battery
say,
capacity.
correct.
Okay, so in the battery capacity is the energy that is stored, that you are replacing. Okay, when you are trying to replace, don't waste even one zone.
No, but if I have a heavy vehicle, why do I have to spend energy in hauling a motor which is 2-3 times size? I'm adding weight.
True, but you are doing the other one also. Anyway, what means same? Wastage in bulkiness.
See here, I show you.
This is only my fundamental thinking.
See, this is your this is the torque application. Okay, what you have here is essentially an electric vehicle is accelerating. So you have torque being applied. Okay, torque being applied here, which is on this axis. So our motor produces 55 Newton meter of torque. So if you see 55 Newton. The speed is right here. So if you look at the velocity is starting from 0. Okay, it's accelerating. So velocity is going slowly up. Okay, just like you can, right? That's how you do it.
Actually, the impulse characteristics only they will try to see that this much speed, this much torque.
Yeah. Well, that's a torque speed. That is that. Okay, this is torque speed. This is the torque speed which has been generated using PSpice. Okay, the blue area, the yellow and the red. The blue is the allowed operation in the US. The yellow is the allowed operation in Canada, and the red is the allowed operation in Europe.
But how do you go to constant power?
What is the limit for that? Why?
Red is 250 watt, yellow is 500 watt, and this is 750 watt.
You mean that much acceleration you are not, or that much power you are not?
Yeah, you can't have, so in Europe, you can't have more than 250 watt of power.
Otherwise you need a license.
Okay, then you need a license. In India also, you can't have more than 250 watt of power.
How do you go to constant power?
See, going to constant power is not that difficult. Essentially,
So this is only you are trying to be within the.
I got a priority.
pardon?
I got a priority.
You got what?
I got a priority. So how do you go to the constant power?
Well, see, the constant power essentially, when you are, you automatically vehicle goes to constant power. Okay, why? How does it go to constant power?
It goes generator, like when it goes.
See, look at this chart here. Look at this chart here. This is torque. This is torque. See how torque is going down. Okay. Look at the power. Okay. Power is now constant here. So once you are out of your initial acceleration, most vehicles automatically go into constant power. Okay. So this is, if you can see the power, you supply the power, and then of course you're also limiting the power. You're also limiting the peak power is limited either by the current limiter. You say, okay, I don't want to supply more than this current.
So actually you purposefully force the current limit to go down above certain speed. That's it, right? Or you phase shift it and go beyond the base speed of the motor.
See, once the vehicle is accelerated, it requires very little power. It requires very little power in terms of, yeah, but you have, if you continue to accelerate here, right, you need power. So the power, but the maximum power which can be supplied by the system is this, which is about 1000 watts, right? It's limited to 1000 watts. Right, now how do you maintain that constant power? You don't maintain it. You only are concerned in an electric vehicle, you're only concerned whether thermally you have a problem or you're exceeding the current, right? So maximum phase current you control. You say, okay, I will not allow more than this phase current. I will not allow more than this battery current, right? So anytime you hit the limits, you slow down the duty cycle.
So unlike induction motor, you are not changing any phase of the current. It's just in phase of the back EMF.
You do change the phase of the motor when you want to go even higher speed.
But just an advanced angle, so that not really phase correction, right? It's just advanced angle.
That's the same as phase advance. Same as phase advance, which will allow you to go at higher speed. But the motor becomes a whole lot more inefficient because now you're drawing a whole lot more current, right? So you're not purposefully limiting the power, but you're purposefully limiting the phase current, the temperature, the battery current, so that none of these limits are exceeded. So you allow people to accelerate as fast as they can without damaging the motor. Okay, so this here is essentially the vehicle characteristics, vehicle performance data based on the same motor. And this motor uses this torque speed curve. All of this curve has been developed using PSpice. Okay, so let's go back to the model. Okay, so we have KE. KE relationship is defined here in an E table. So KE value goes from 0.472 to 0.287 at that value. Okay. So once you have that, let's see. So here is your actual PI loop. The other part we do is, now the other challenge you have is how do you generate current reference? The current reference has to be proportional to the position, right? Because the current reference has to has to match the position. If you don't match your current reference with the position, then the current reference will not match the back EMF and the motor will not rotate. Correct? Correct? So this is your position, right? Your back EMF is like this. That's your back EMF. Right? So when I'm trying to control the motor, I got to have current which is in phase with the back EMF. Right? So I have to know how the back EMF is aligned with the position and how to generate this current. Right? So the current reference has to be generated from your position signal.
So when you say both are sinusoidal, it's more of a PMSM than PIDC, right?
It doesn't, my shape doesn't matter. Shape really doesn't matter.
It is a sensorless control, eh?
No.
No, not sensorless.
Sensors are there.
Then why? If you sense the voltage, you can accordingly commutate the current.
Current is 180 degrees, no?
Huh?
Current is 180 degrees.
No, not current. See, what to switch the things in the proper phase with the vector control. Okay?
Based on the current, you have to estimate the position.
Huh?